go. All right, this was the title that someone or other gave me, and it'll do. So I thought I would tell you a little bit about the Sense Foundation before I go on to the main body of the talk. But anyway, the Foundation is, as I've said, a US-registered charity, and we work to promote and to make happen the development of regenerative medicine solutions to the disabilities and diseases, the ill health of aging. And I'll be talking about what that means in practice through this talk. We do actually now have an in-house laboratory. We've had one for about a year, and it's growing, and it will almost certainly be moving very shortly to Sunnyvale. It's currently in the Phoenix area, which is not the ideal place for something that is quite so cutting edge. And we feel that it will benefit enormously from moving over here. But it is populated by the most extraordinary bunch of talented and unbelievably committed youngsters who are really generating results at the most extraordinary rate with unbelievably little amounts of money. So that's one thing we're doing. And of course, in addition to that, we have a variety of extramural activities funding laboratories in universities around the world. And of course, we're interested in educating people about things, so I gave an insane number of talks, probably about one a week, to a wide variety of different audiences, most of them rather less informed about this whole topic than you guys, but of course it's important to tell everybody about this because we've got to get the scientists interested, we've got to get wealthy individuals interested, we've got to get everybody interested in all of this. All right, so I'm going to talk today, 99% of what I'm going to say is about how we're going to do this. But I thought I would just start by reminding you why we're doing this. And it comes down to what I've got on this slide. A lot of people, especially a lot of journalists, like to characterize my work and the Sense Foundation's work as being about immortality or living forever or other entertaining but obviously fictitious concepts. But actually what we're about is stopping people from getting sick, which is a very down-to-earth and not terribly controversial topic. And the only real thing that distinguishes Sense Foundation and my proposals for how to do this from those of the rest of medicine, certainly the rest of people working on age-related diseases, is that I think we can do it really, really well fairly soon, like in the next couple of decades. But by developing a very comprehensive range of treatments for the various things that go wrong as we get older. Whereas most people are satisfied with essentially tinkering around the edges and trying to delay by the odd few years one or another of the major problems of aging as if that were equivalent to actually solving it, which I certainly don't feel that it is. I want people just not to get into the state characterized by the photograph on the right, however long they live. So what I'm going to do today, as I say, is talk about how we're going to get there. And it's going to be split into these major themes. I'm going to first of all just start at the 40,000-foot level and discuss the conceptual basis for what sort of approach to combating aging is the most promising, namely, as I've said already, the essential application of regenerative medicine to aging. Then I'm going to get down a little bit into some real biology and talk about what that means at the molecular level, at the cellular level. I'm not going to get very technical here. I know that this audience has a very wide range of degrees of expertise in biology, so I'm not going to try to lose too many of you at this stage. I may lose some of you in step 3 of the talk, where I will get into a bit of hardcore biology and generally convince those of you who are experts in biology that I'm not completely bullshitting you all. Then after that, I'm going to move from science to technology, and this is going to get into territory that's much more singularitarian, shall we say. But as you will see, it is much less controversial, relies much less on uncertain concepts than the classical singularity concept of accelerating change. So I'm going to be talking about this concept that I've coined the name longevity escape velocity, and you will see that it's pretty inescapably going to happen, because I'm going to talk about how we can quantify that thing, and you'll see that it's very modest indeed. And finally, I'm going to talk a little bit about what you guys can do. I've already done something by being selected for this course, I can tell you that. So I'm going to start here with the very general top-level analysis. Now, of course, we're talking technology here, and as with any ambitious, pioneering technology, the first step is to define the problem, or perhaps slightly better, to describe the problem in a manner that is conducive to identifying how promising a given candidate approach to solving the problem might be. And after some deliberation, this is the definition of aging that I came up with a number of years ago that I think is particularly helpful for doing exactly that, for identifying why we might be able to do something about aging and specifically how we might be able to do it. So we all know that aging is a side effect of being alive in the first place. Okay? If it were just independent of aging, then it would happen to people independent of their age. And actually, it only happens to old people. So we know that, ultimately, metabolism causes pathology. I'm using metabolism to denote the entire set of all the metabolic, the cellular and molecular and metabolic things that happen every day, all the time in our bodies that just keep us alive from one day to the next. And it causes, eventually, pathology. In other words, all of the aspects of age-related ill health. Now, what I'm doing in this definition here is I'm defining a third term, namely the term damage. I'm defining it, as you can see, as the set of intermediates between metabolism and pathology. So I'm basically saying that we need to concentrate on what you might think of as the initial byproduct, the initial side effects of metabolism. Pathology is an eventual side effect of metabolism, but we can define it as a process of lifelong accumulation of various immediate side effects that, when they get sufficiently abundant, cause bad things to happen, get in the way of metabolism, if you like, and stop it from working so well. So damage accumulates throughout life, even starting before we're born, and only once it becomes sufficiently abundant does it actually do us any damage to speak of. So why is that so useful? Well, it ultimately comes down to this sort of concept here. I've got here metabolism causes damage, causes pathology. Now, historically, there have been two ways of looking at the problem of aging, insofar as anyone even thinks of it as a problem, which is, of course, not nearly so universally accepted as it ought to be. One of the approaches is what I'm going to call the geriatrics approach. And that is simply to say, well, OK, let's see what's going wrong in an older person, and let's try and attack those particular pathologies head on. Let's try and actually identify those things at a relatively early stage and try and slow them down, try and hold back the sands of time, so to speak, and delay the rate of progression of pathologies, thereby, of course, postponing the age at which people get to a point where the pathology is life-threatening or seriously handicapping. That's the geriatrics approach. Now, that's one approach. OK. There's another approach, which is the gerontology approach. And essentially, gerontologists feel, well, actually, prevention is better than cure. The geriatrics approach is better than nothing, but maybe will be more effective by trying to get in at an earlier stage of the chain of events and try to clean up metabolism, try to stop it from laying down these various lifelong, ongoing types of damage at the rate that it would naturally do so, and thereby, of course, having the same effect of postponing the age at which the damage reaches a pathogenic level. So that's all very well. So what do I think of these two approaches? Well, to be honest, not very much. And furthermore, I haven't yet said anything controversial. Don't worry, I will. So here is the problem with the geriatrics approach, of course. You don't need to be a biologist to know that aging is really not very nice. Lots and lots of things go wrong. They go wrong in a very chaotic manner. They exacerbate each other. It's all completely hopeless. And the worst of it, of course, is that because we are attacking these eventual consequences of the accumulation of damage, what we are essentially doing is addressing a problem that's getting harder as the person gets older. So the geriatrician's job is constantly becoming more and more challenging for a given patient. And, it's hopeless. Basically, this tells us that the geriatrics approach, yes, it's better than nothing, insofar as we can actually do anything that way, but it's not much better than nothing, and it never will be. It is intrinsically kiboshed by the inability, but by the fact that it's intervening so late in the day, that it's not intervening in the ongoing problem, but rather in the eventual consequences of it. Unfortunately, the gerontology approach isn't a lot better, and this is why. Metabolism is quite complicated. Now, this is a simplified diagram of a small subset of what we know about how the body works, okay? And that's bad enough. But of course, the really bad problem is that this is a small subset of what we know about how the body works. And it is completely dwarfed by the astronomical amount that we don't know about how the body works, let alone all the probably even more astronomical amount that we don't even know that we don't know. So So basically, it's hopeless. There's only so much that you can expect to achieve by tinkering with a machine about whose operation you are this profoundly ignorant. It's just hopeless. And again, I want to point out that I have still not said anything with which any self-respecting biologist would disagree. Okay, so this is why gerontologists and people in general who study the biology of aging have come to this ridiculously fatalistic conclusion that you might not even bother, you're wasting your time even thinking about doing anything decisive about aging. We just don't know enough. All we can do is hack away as basic scientists trying to discover more and more about how the body works and how aging works, and eventually we will understand metabolism well enough that the gerontology option for combating aging may actually be feasible. But that's not true. Now, before I go on to why it's not true, I want to address something that those of you who know a bit about life extension and who pay attention to the popular press in this area may be thinking at this point. You may be thinking, well, hang on, this sounds logical that the gerontology approach is impossible because metabolism is too complicated, but we keep hearing these reports about successful extension of the maximum lifespan, not just the mean lifespan, of respectable species, like mice even, using relatively simple methods that are already possible, like, for example, calorie restriction. I don't know how many people in the room know about that. Hands up anyone who knows what calorie restriction is. Good, fantastic, nearly everybody, great. So the question then is, okay, what's the catch? How come we can do this, but yet I'm standing up here telling you such pessimistic, fatalistic rubbish about gerontology? The ultimate answer is it doesn't scale. There are a number of reasons why very simple interventions, which I'm going to call magic bullets, will not be an appreciably useful answer, not for human aging anyway. This is the biggest one, I think. Essentially, magic bullets only work if they are the flipping of a switch that activates a whole bunch of machinery that's already present in the body. Metabolism really, really is as complicated as I just said it was, and that means that aging really, really is also that complicated, because aging is fundamentally the accumulation of the degradation of function at all levels of organization in the body. So you've got to do an awful lot of things. You've got to change an awful lot of things in the body in order to slow aging down. So a magic bullet that only changes one thing is only going to work if it somehow activates a whole pyramid of downstream things. The question then is, why does that pyramid exist? Why is that? Why do such master control genes exist? And the only way that that can actually happen and can be maintained during evolutionary time is if the genes that mediate that complex machinery are selected for and are maintained despite the constant pressure of accumulating random mutations. Random mutations that are not selected against are going to accumulate, and the machinery is going to mutate into oblivion. So something's got to be stopping that. And it turns out, if you think a little bit through the details of this, I don't have time to go into the real details, but of course this is published. I can send you stuff if you're interested. It turns out that the longer lived a species naturally is, the less effective evolution is going to be at maintaining such machinery. So shorter lived species have more impressive metabolic acrobatics encoded in their genomes to respond to environmental challenges or whatever than longer lived species do. And that's why I think that, for example, calorie restriction itself is probably only going to give a couple of years of additional lifespan to humans, even if started really early in life, and that drugs that emulate calorie restriction are not going to do any better, and that anything that might be slightly different, like you've probably heard about the rapamycin experiment on mice that was published quite recently, it's basically, again, the same story. It's just not going to work very well in a long-lived species like you and me. Another problem is this, that evolution doesn't select well for things that are only useful late in life. It only selects well for things that are useful early in life, because that's when the organism is breeding, and that's what matters from an evolutionary perspective. And sure enough, calorie restriction, when started late in life, only gives proportionally about the same amount of same extension of remaining lifespan in mice, for example, not the same amount of total lifespan. No surprise, but I think it needs emphasizing. So those of you who have the misfortune to be old enough to pay for this course probably won't actually be able to get as much benefit as your kids. So that's a bit of a shame. However, this is the real kicker, right? The fact is, if you're already getting on, you probably are already jealous of your kids with whom you can no longer keep up on the dance floor, right? So it would be awfully nice to fix that, and actually to have people maintaining young adulthood, even if they had already slipped a little beyond that already. What's the catch? Why am I here? Why am I actually optimistic? Well, here's where that story starts. The human body is, at root, a machine. It's a really, really complicated machine, but we all know, there's no dispute about this, the human body is a machine. And machines accumulate wear and tear. Machines have what you might think of as a warranty period. They're built to last a certain amount of time, and they probably won't last much longer than that, other things being equal. Here is a machine that has lasted unusually long for a car. This is more than 50 years old, and the reason it lasted that way was because it was built unusually well. Its warranty period is that sort of time. Obviously corrosion-resistant metal and really strong tires and all those things. Now, that's one way to make a car last longer than the, let's say, 10 or 15 years that your average car is likely to last. But the thing is, there's another way to achieve that sort of longevity for a car. You don't have to build it with a warranty period of 50 years in order to make it last 50 years. And that's why I said VW bugs up here, because of course there are just as many 50-year-old VW bugs driving around the streets of the USA as there are 50-year-old Land Rovers. And the reason is because they've got style. And their owners have fallen sufficiently in love with them that they have done enough maintenance on them to keep them, comprehensive enough maintenance to keep them going. This car was built in the same year as the one on the previous slide. It's doing just as well as it was when it was built, and it's likely to be doing just as well for as long as it carries on being maintained. So what we are learning here is that if we know how to do sufficiently comprehensive maintenance on a machine, then it's going to last. Maintenance actually works. So the question then is, what does this mean for the human body? This is fundamentally what it means. There is a radically different third way, a third approach to postponing aging and keeping people healthy. Rather than trying to intervene in this process here, whereby metabolism ongoingly lays down all this damage, or trying to intervene in this process over here, where damage eventually causes pathology, what we do is we intervene in the damage itself. I like to call this the maintenance approach. You could call it the engineering approach. You get the idea. The point here is we let the damage happen, and we get rid of the damage. We repair the damage periodically so that it never reaches the level of abundance that causes this bad stuff to happen. And I want to belabor this a little bit. I want to explain why this is such a promising approach. It's really pretty simple. It comes down to the fact that the maintenance approach avoids the shortcomings of the other two approaches. It gets the best of both worlds. On the one hand, it intervenes early enough in the chain of events that it doesn't have this problem of a progressively harder and harder problem as the person gets older. Damage, by definition, does not have any accumulating precursors. It is simply the ongoing, lifelong side effects of metabolism. But secondly, and perhaps even more importantly, the maintenance approach intervenes late enough in the chain of events that we are getting away from the problem of complexity of metabolism. What we're saying here is that we're going to let metabolism lay down these various types of molecular and cellular damage, and we're going to let metabolism do that at the rate that it naturally does it, okay? Which means that we're not going to need to understand it very well. All we're going to need to understand is what the damage is. We're going to have to characterize that damage and figure out ways to repair it, or in some cases to make it harmless, make it no longer cause pathologies. But we don't have to do anything about how it's caused. So we can essentially escape all of that problem. We can sidestep our profound ignorance of how metabolism works. All right, well, that's all very well. That's the 40,000-foot view, like I said. And those of you who know a bit of biology may have noticed that I have said almost no biology so far, apart from telling you how nasty and complicated we are. So I'm going to change that in a moment. I've so far only told you one reason why the maintenance approach is so promising. Namely, it seems to target what you might think of as the weak link in the chain of events that go from being alive to being dead. But there's another reason, which is damage is not actually nearly so complicated as either its causes, metabolism, or its consequences, pathology. this is my first outrageous statement of the day, that we can, in fact, classify all of the molecular and cellular phenomena that qualify as damage by the definition I'm using today into these 7 major classes. So the definition is, remember, ongoing, accumulating side effects of metabolism that eventually contribute to age-related pathology. That's the definition of damage, and I claim that everything that we have good reason to believe qualifies is in one of these types of category. So what's the first one? What does that mean, junk inside cells? It simply means molecular byproducts of some metabolic process or other that the cell, for whatever reason, doesn't know how to break down and doesn't know how to excrete, and so it just sequesters the stuff. And the stuff just sort of doesn't get in the way at all. It's completely harmless for a long time, but eventually it's a bit like not taking your garbage out for a year, and the house doesn't work so well, similarly in the cell. Too few cells. Well, I have a feeling 1 or 2 of you in the room have heard of stem cell therapy. Stem cell therapy is, of course, basically the idea of solving this problem. When in the body, as it naturally is, a cell dies, and for whatever reason it's not automatically replaced by the division and differentiation of other cells, then the number of cells in the tissue gradually goes down, and eventually there are pathogenic consequences of that. So stem cell therapy is about fixing that, about putting cells back when the body's not doing it on its own, so that the cellularity of the tissue remains useful. And you can go down this list, and it's all things that you've heard of. Pretty straightforward stuff. Now, of course, the outrageous statement is that this is comprehensive, that actually there is nothing more than this, no 8th sin, so to speak. And one reason for saying that that's true is this. It's circumstantial, of course, but it's a pretty profound point. It's been the same list for more than a quarter of a century. You know, we've come a very long way since the early 80s in our ability to analyze biological systems, figure out what they're doing, what they're made of, and all that. You know, we would have added to this list, it seems to me, if there were stuff that was waiting to be added. So that's good news. But of course, we can go further than that. I have a question at the back.
What about damage to individual cells? So after a certain period of time, a cell will just spontaneously die because it's becoming damaged in different ways.
Well, OK, so I'm classifying the damage as the cell death rather than the damage that causes the cell death. So the question was, like, what about damage to cells? So what about simply damaged cells? Now, some of these things do qualify as damaged cells. So, for example, when junk is building up inside a cell, you know, the cell is in some way damaged, in a way that it will eventually, when the junk gets too abundant, be problematic. But if the cell just dies, which is what you just asked, then it's not a problem at all if the cell is replaced by the division and differentiation of another cell, of a stem cell, for example. But if that doesn't happen, then you get this problem, too few cells. So that's how one can come up with this sort of list. And I was actually about to answer the question slightly more generally. I'll come to you in a moment. Slightly more generally, we can come up with this list by a very simple metric. We can simply say, well, OK, if, let's say, a protein is created in a cell and it gets oxidized and then gets detected as being damaged and gets broken down, that doesn't qualify as damage by the definition I'm using today, because it can't accumulate. The damage is gone once it's been oxidized, once it's been got rid of. So damage, what this means is damage can only accumulate in long-lived structures. And so one can just go through the body and say, well, OK, what are we made of? We're made of cells and stuff between cells. What are cells made of? And so on. And you can get this list, basically, out of that. You're worried about fluctuations that may happen in the metabolic state of a cell or an organ or whatever. Now, absolutely, fluctuations like this happen all the time, and indeed it's a damn good thing they do, because what our body experiences from one moment to the next varies. For example, I'm experiencing beer now, which I was not experiencing when I got here and asked for it. And you know, these things change what the body does, what different cells do, and the body has to respond to that. So basically what we have is a homeostatic zone, a range of environmental conditions and internal conditions of the body and of individual organs and cells that the body knows how to handle and to bring back within range to the extent that it needs to. So blood sugar, for example, insulin response to that, to keep it to a basal level and not get out of whack. And the reason these things get out of whack is as a consequence of the loss of homeostatic function that results from the accumulation of damage. So the reason that age-related problems are age-related is because of loss of the ability of the body, of metabolism, to do what it normally does. And you're quite right that a lot of what metabolism does is maintaining homeostasis in the face of fluctuating conditions. I hope I've answered your question. Maybe I'll answer it better when I get on to a bit more. All right. Anyway, so this is the list of things that I think we need to fix. Now, that's good news already, if it's true. But as I say, I mean, some people might say that this might not be a complete list, but I think it probably is. Here's the really good news. We have a fair idea how to actually fix these things. So here, I'm listing the same things on the left that I just listed before in a slightly different order. And the things in the right-hand column are the approaches that I think are the most promising for actually addressing these things. And when I say addressing, again, I do not mean slowing down the accumulation or the exacerbation of the problem. I mean actually reversing that accumulation, or in some cases obviating it, fixing the effects of the problem. So I've just mentioned stem cell therapy already. Hang on, it won't be a second. And I'll talk about one of these in much more detail in a moment. The key thing I want to say on this slide is, obviously I'm just naming things here, but we have reasonable amount of confidence that we will be able to implement these things, and where we get that confidence is because of the detail with which we can describe what these things mean. So the book I published a couple of years ago has an entire chapter on each of these things. That's really important. In any technology, the more detail you have about how to fix how to implement the parts that you haven't implemented already, the more confident that you can be about the time frames within which you might be able to implement those things. Whereas if you can only say in very broad strokes what you need to do still, then of course your time frame predictions may be very unreliable. And I don't think that we're going to get these things working perfectly anytime soon, but I think within the next couple of decades we have a pretty good shot at getting them to work well enough to give middle-aged people 30 additional years of healthy life. And so the question is, to what extent do these problems and their solutions interact? Will we achieve any sort of impact by solving only half of them? And to be perfectly honest, we don't know. The chances are that some of them are more they have their tentacles in more pathology pies, so to speak, than others. And so we may indeed get more of an impact in some places than in others. I think mitochondrial mutations is probably the big wild card in all of that. There are a lot of people in gerontology who are still pretty unsure whether mitochondrial mutations actually matter at all, actually contribute to pathology in a normal lifetime in mammals. Whereas there are other people who think that they are probably the single most important thing and that they have indirect impacts on more or less all the pathologies of aging. So this is a big wild card. The other ones, we can point to individual types of pathology, like, for example, cancer in the case of nuclear mutations, or atherosclerosis in the case of intracellular junk, and so on. We can point to things where we know that the pathology happens, and it happens at a normal lifespan, which is why a lot of people die of it, and it's primarily caused by one or another particular one of these 7 types of damage. So in those cases, we can say fairly clearly that if we don't affect the rate of accumulation, and we don't end up being able to repair that particular type of damage, then we will not have much effect on average longevity, because that particular cause of death, that particular pathology, will come along at more or less the age that it comes along today. So that sort of answers your question. It's a lot that we don't know, but certainly my goal is that we should indeed implement all these things as soon as possible and get the real McCoy. All right, so because I've only got an hour, obviously I can't talk about, I've only got, bloody hell, in theory I've only got 20 minutes left. I obviously can't talk about these things in a lot of detail. Read the book if you want to know more, or ask me to give a talk or whatever, but I will talk about one of them in more detail, just to give you a feel for the fact that we really know what we're talking about, and also because it's dead glamorous, this one, and we're working on it very heavily in our intramural facility, in our research center that's moving to Sunnyvale, and also actually in 2 of the labs that we're funding extramurally. It's the thing that we're putting the most money into. The reason we're doing so, this one here, intracellular junk, is because it's one of the ones that needs the most support. The approach that we're taking is very new. It was something that I came up with less than 10 years ago, and it's only had a few papers come out so far on it, but everyone who hears about it thinks, wow, that would be cool, wouldn't it? So first of all, let me explain the problem. I mentioned briefly one of the diseases that are caused by the accumulation of intracellular junk, but there are a number of them. Here is an electron micrograph of a slice through an axon of an Alzheimer's neuron, and as you can see, it's not very pretty at all. This is basically the signature of failed degradation of stuff. things that ought to be getting broken down, and they're getting what's called autophagocytosed, but not a lot else is happening. That's the sort of preliminary step towards getting something broken down, and the whole thing is stalling at that point. That's in Alzheimer's disease. In atherosclerosis, it looks like this, and it looks completely different. You've got different types of junk accumulating, but at root it's exactly the same problem. You've got this thing called the lysosome, which is the part of the cell that you can think of as the garbage disposal machinery of last resort in the cell, and it's not working anymore. It's been basically poisoned by the accumulation of stuff that it can't break down. And this is a foam cell, which is the first histologically detectable stage of the development of an atherosclerotic plaque. All right. Now, the idea I started to put forward about 10 years ago is this, and it comes from a field that had nothing to do with medicine, from a field that is completely divorced from medicine at the moment, called bioremediation. Bioremediation is a field within environmental decontamination, and it is founded on an idea that was first put forward over 50 years ago, which goes like this. It says basically, you would expect that in nature, when you go to a particular environment, you will see only a small number of microbes in that environment because they'll be the ones that were able to grow fast on the things that were there to live on. But in fact, that's not what you see at all. More or less anywhere you go, you see a very wide variety in the microbial ecology. And the proposal was that this is because there are some things in most environments which are really hard to break down, but which, if you can break them down as a bacterium or whatever, you can live off them. If that's true, fantastic. Now, there's a lid on this. Someone find me a bottle opener. I'll have to do this myself. All right. Now, if that's true, then the question is, what effect would that have on the variety of the microbial ecology? And the answer is, of course, quite a big effect. What it would do is, it would mean that there would be bacteria out there that were intrinsically not very fast-growing, but they would have the ability to break down something that their faster-growing colleagues could not break down. And if they could do that, then bingo, they've got their ecological niche, and you're going to find them. So the guy who thought up this concept, which he gave the wonderful name of the microbial infallibility hypothesis, he said, well, more or less anything that you look for that's a pollutant, which is abundant in some environment, and it's also energy-rich, and it's organic, of course, more or less anything that you look for that you want to get rid of in the environment, let's say it's TNT in the soil on a disused airfield that you want to build a housing estate on, what's going to happen is you're going to be able to go to that environment and you'll find that there are bacteria in that soil that are already chomping away on the TNT. And the only reason there's any left is because there are not enough of those bacteria. So you can find them, you can get them out, you can expand them in the lab, put them back in the environment, the TNT goes away, you can build your housing estate. It works. Bioremediation is not just an academic concept, it is an extremely thriving commercial enterprise. So, the question is, what does that mean from a biomedical point of view? So the idea was this. I realized that there are environments that are enriched in human remains. And of course, that means that they're going to be enriched in exactly the substances that accumulate in the human body and cause these horrible diseases. So, you know, they are exposed to the environment after burial. Now, interestingly, we don't see them in graveyards, those substances. We do see bones and teeth, but of course, bones and teeth are not energy-rich, so you're not going to be able to live off them if you're a bacterium that can break them down. So that doesn't in any way invalidate the microbial infallibility hypothesis. They do not accumulate these things that I was talking about a moment ago. So a very plausible interpretation is that indeed the hypothesis is correct, and microbes are in the graveyards and they're breaking these things down. So what use is that? Well, of course, the possibility is that we could find out how they're doing it. I am certainly not suggesting that we should find these bacteria and then inject them into the body, you know, so to break down these things. That would probably be counterproductive. But I am suggesting that we could go and find out the genetic basis for their capability, for how they're succeeding in breaking down these things. And having done so, we could put those, maybe not very many genes at all, into our own cells, into particular cell types, and thereby augment our natural ability to break molecules down, so that things that we can't naturally break down will not, in fact, accumulate. And indeed, anything that has accumulated will go away. This is the idea in a simple diagram. There's a natural process in the human body that turns young people into old people, and eventually to dead people. And then there's a completely different process in the microbial ecology of the environment, which turns dead people into decomposed people. And what we do is we simply figure out how they're doing it. We do some laborious but nevertheless relatively standard molecular biology, and we manipulate our own cells. This is my absolutely appalling diagram of a neuron, and thereby slow down or indeed combat the process that turned young people into old people in the first place. And the thing is, it does actually work. So here is a sample, a representative experiment from a paper that we published last year. This was the first paper that came out of funded efforts, and there's a whole slew of them in progress at the moment. A couple more are out already, actually. What we've got here is we're looking at this particular chemical here. 7-ketocholesterol is one of a large number of different oxidative modifications of cholesterol that one can find in the human body, but this one is probably public enemy number one in atherosclerosis. It's rather abundant, and it's very, very toxic. So we've got a whole bunch of bacterial strains here, and we give them this stuff, and we don't give them anything else to grow on, so there's selective pressure to see what's going on. And most of them can't do bugger all with it, and they just hang out there, and the 7kC doesn't go away. But two of these strains, as you can see, are having a fantastic time, and after only 10 days, the stuff's almost entirely gone, and you don't need a microscope to see the result. You can just look at the Petri dish. So that's very nice. And of course, the next step then is to figure out what's going on. There are a number of ways to determine how a given bacterial strain is breaking down a given substance. This is one approach, mass spectrometry, which essentially says let's find out what they are breaking it into, what are the breakdown products of the substrate. And this is the sort of thing we're seeing, and that's the first step into identifying what enzymatic reactions are occurring in the thing. Now, I am not going to try to tell you that this is easy. This is a very long project. What we've done is we've demonstrated that it's not terribly hard to do step one here, to isolate strains of bacteria that can break down things that we would rather not accumulate during aging. Number two is where we are at the moment. We're doing a lot of identification of enzymes that have these interesting effects, and we've identified some very important ones for a third age-related disease that's very important in this area, which is macular degeneration, the leading cause of blindness in the elderly. We're also in the process of identifying good enzymes against 7-ketocholesterol, so that's good. But after that, there's a hell of a lot more to do. We've got to actually get these enzymes to work in mammalian cells, which may take a fair bit of tinkering to make them work at different pH, things like that. We've got to make sure that they don't break down things that we would prefer not to have broken down. That may sound quite challenging, but actually there are plenty of tricks for that. But it still takes time. And then, of course, we have to get into mice. We have to get into live animals in the lab and see how the whole thing works there. And it's only after all that that we can get to clinical trials. We can even think about clinical trials. So this is a long project. But let's face it, that's OK. Because as and when this works, it's going to be so astronomically more effective against these viciously prevalent and nasty diseases of aging than anything we have today, or even anything that's coming down the pike. So much more effective that it's going to be worth it. It's going to be none of this bloody, reaming out arteries and putting stents in and so on. This is going to be the proper job, removing the root cause of the inflammation and clogging that goes on during life. And, so the sooner we start this very ambitious long-term project, the sooner we'll finish, and that's why we're putting so much effort into it, and why I'm so proud to be leading the scientific component of an organization that's pushing that. Daniel.
If this process works perfectly, what do you think, on its own, what effect will that have on, if you did this therapy on a mouse and then on a human? What's your best guess of the effect on its own?
Okay, so the question from Daniel is, supposing we just did this removal of lysosomal junk, of intracellular junk, and we didn't do any of the other 6 components of the SENSE program, what would be the impact on health, on how long people would stay healthy and on how long they would stay alive? So this is related to the question that was asked earlier on, of course. Now, of course, what your question really is that this would be done on all tissues for which the accumulation of junk is a problem. So that certainly means the artery, it certainly means the brain, it certainly means the eye. The best bet in the Western world, of course it varies from country to country, the best bet in the industrialized world is that roughly half of the causes of death and causes of morbidity in the industrialized world are caused by that range of diseases. So that means we'd be looking at roughly increasing the healthy lifespan and the total lifespan by what's called the mortality rate doubling time, by one mortality rate doubling time. The amount of time, the age at which n% of the people die in a year to the age at which 2n% die. And that time is roughly 7.5 years. So a reasonable amount, but sure as hell not a complete solution. Essentially, after we've got rid of all that, the number one killer by some distance would be cancer. And cancer is not going to be appreciably affected by this particular intervention. And diabetes may be somewhat affected, but cancer's the big one. All right. Here we go. So that's the hardcore science part. And for those of you who'd like some more hardcore science, talk to me afterwards, or buy my book. I'll show you more about that later. But I'm going to get on now and move away from biology per se and talk more about technology. And specifically, I'm going to talk about the history of technology. Can somebody tell me by how long I am entitled to overrun? When do you really want me to stop talking? I'll take at least another 10. Great. All right. Thanks, Daniel. All right. So longevity, escape velocity. So what I'm going to do here is I'm going to talk about what happens next. Those of you who were paying really close attention earlier on will have seen that I did not say that doing all of these things, even, well, certainly not to the extent that we're going to be able to do them in the next 20 or 30 years, will completely solve aging. What I said was that it will solve aging comprehensively enough to deliver perhaps 30 additional years of life. Okay? And that is not defeating aging, certainly not by sorts of standards that those of you who are familiar with the singularity would think of it. But it's a good start. Why, therefore, do I tend to be described in the media as the millennium man or whatever, or the prophet of immortality? The answer is because of this one down here. I've told you so far 2 reasons why the maintenance approach is so extremely cool. It targets the weak link in aging. The weak link is not only weaker, but also simpler. This is the third one. The repair and maintenance approach buys time. And I'm going to tell you exactly what I mean by this. And I'm going to be able to go through this pretty quickly because I know you guys are sharp. Here I'm doing, in a very schematic manner, a description of what aging naturally is and what we can do about it with therapies that are of the nature I'm talking about today, repair and maintenance therapies. So the red line here, this one here, is simply natural aging. Basically what I'm saying is that age is along here, and on the y-axis I've got reserve. Now reserve is simply the inverse of damage. So I'm saying you start off with lots of reserve, not much damage. You accumulate damage, you lose reserve. So reserve is essentially the amount of additional damage that you can afford to accumulate before pathology sets in. The dotted line here, which I'm calling the frailty threshold, is where pathology sets in. So I'm not trying to tell you that aging happens at a uniform rate or anything. This is, as I say, very schematic, but I'm just wanting to get a concept across. These therapies are going to be applied to people who are already in middle age, not to people who are in childhood, who have not yet been conceived or anything like that. People in middle age. And the reason is, of course, because they are repair and maintenance therapies. You don't take a brand new car into the garage the day after you bought it. So the pink line here is what I've told you so far. We're going to take someone about here who's, let's say, 60 years old. We're going to fix up their damage fairly well. We can't do it perfectly yet, but we'll fix up maybe half of it. And of course, as has come up in a number of questions, that means fixing all of the various types of damage reasonably well. We can't afford to leave any of them completely alone. Maybe half the damage, like for sake of argument. We don't alter the rate at which the damage is created, remember. We're not interfering with metabolism itself. So after that, damage accumulates, reserve diminishes at the rate that it already was, the same gradient as the red line. But of course, we can apply the therapy multiple times, and that's what I'm saying with this zigzag line here. Problem is, we hit diminishing returns. We can do this more and more often, but we get less and less effect. And eventually, the guy falls over the frailty threshold anyway. Why? Obvious reason, because of the damage that we're not fixing, the damage that the therapy doesn't work on because it's not yet perfect. What's happening is that that damage is accumulating unabated, such that eventually, on its own, however well and however thoroughly we are fixing what we might call the easy damage, the difficult damage will be able to tip the individual over the frailty threshold, and the rest is history, so to speak. So that's a big problem. And if you and I were mice, such that the x-axis here, on which I have carefully put no numbers, went like 1 year, 2 years, 3 years, then that would be the end of my story. But we're not mice. We have maybe 30 times as long a lifespan as mice, which means that the interval between the first and second applications of these rejuvenation therapies is going to be maybe 20 years. Now, 20 years, as I am sure has been impressed on you rather heavily during this course, is a hell of a long time in technology. So, we can actually say that the pink line here is not realistic. What's much more realistic is that when our hero comes in for his second rejuvenation, 20 years after the first one, he or she will receive a therapy that's been improved, not only in convenience, not only in cost, but also in comprehensiveness. So that the therapy will, of course, work on all the types of damage that it worked on before, but also, in addition to that, it will work on some proportion, let's say, for sake of argument, half of the types of damage that it could not work on before. So that's this line here, the first part of the orange line. And as you can see, that's qualitatively different in the long term. What we're achieving here is that our hero, after his second rejuvenation, is actually at a younger biological age than they were after their first rejuvenation, even though chronologically they're 20 years older. And, of course, this concept can be iterated upon, such that in the long term these people get chronologically older, of course, but they get biologically younger, and they never go anywhere near the frailty threshold. So that is why we can talk about the concept of maintaining healthy lifespan, and therefore, of course, total lifespan indefinitely. So what is longevity escape velocity? It's very simple. It's the cusp. Obviously, there is a degree, a rate of improvement of the comprehensiveness of these therapies that is required so that in the long term, the gradient of this whole trajectory is upwards rather than downwards. And said in words, what that means is this: it's the rate at which rejuvenation therapies need to be improved following the achievement of that first breakthrough of about 30 years extension in order to outpace the accumulation of damage that they don't yet work on. Very simple concept, as you've seen. But it's an important thing to bear in mind in determining what the consequences will be of therapies that are already foreseeable. The final step, of course, is to determine whether this rate of improvement, longevity escape velocity, is actually realistic. I've so far just waved my hands and said, well, you know, it sounds pretty realistic. 20 years is a long time in technology. But let's go a bit further. Let's go and have a look at some actual precedent. We don't have any direct evidence, and the reason why most of my more strident critics within gerontology get terribly upset about the longevity escape velocity concept is because they're fixated on the concept of direct evidence. They're basic scientists more than technologists. They just don't believe in lateral thinking, and they refuse to accept arguments like this as being remotely relevant to the question. But of course they are relevant. This is the sort of thing that we can use to remind ourselves that there are two types of breakthrough in technology. There are fundamental breakthroughs, like what happened in 1903, where the sort of thing that Leonardo da Vinci probably thought was only 20 years away actually finally happened, okay? Namely, the first powered flight. And that was something whose time frame could not be confidently predicted until it actually happened. It's just, that's in the nature of fundamental breakthroughs. But then since that time, we've had a steady and smooth and rather rapid progression of refinements of that, of incremental refinements of that breakthrough, which, I mean, are pretty impressive, really. I mean, I don't think the Wright brothers would have been terribly impressed with the possibility that only 24 years later someone would be flying solo across the Atlantic, but that's Charles Lindbergh, Le Bourget, and, you know, the same is true for the next steps. And we could say, well, okay, where's my flying car then? But of course we know the answer to that. The answer is we can't be bothered. There is not actually enough public pressure, commercial pressure, and so on, to actually do anything appreciably greater, more impressive in powered flight than Concorde. So that's one argument. In order to reinforce this even further, I, along with a guy that you may have heard of, many of you, Chris Phoenix, from the Center for Responsible Nanotechnology, worked on a computer simulation of this whole thing. And to cut a long story short, this is what we came up with. This is all published. Again, I can send you the reprints if you like. The black line here is normal aging. So this is a survival curve, in contrast to the schematic thing I showed you earlier, which was about how healthy an individual is. This is the distribution of ages at death of a population. And this is a typical distribution that you'll see. At age 0, everyone's alive, obviously, and hardly anyone dies until 50 or 60, and then everyone starts falling off a cliff, and hardly anyone makes it to 100. Now, the blue line, the dark blue line that you can see here, is the trajectory, the survival curve of people who get these therapies, but who only start getting them at the age of 80. Okay, now that is, of course, the point where about half of them are already dead, and that's why the lines are coincident until here. But you can see that even the people who are alive don't really benefit all that much, and that's because they're not very well. They're already frail, and there's only so much that these therapies are going to be able to do for such people in the short term. So most people, even the really lucky ones, only get maybe 10 or 15 years of additional benefit. However, look at the next line, this grey-blue line here. This is a rather important line because it's the line, the survival curve of people who are only 10 years younger. They are 70 at the age where the therapies are initiated. And you can see it's the same story at first, but eventually, as time goes on, these people are really showing the consequences of getting biologically younger as they're getting chronologically older. And about 15% of them make it out to 150, and after that, it's a piece of cake. Basically, hardly any of them die, and 10% of them just never, ever die of anything related to aging. This diagram doesn't represent deaths not related to aging. If you're just 10 years younger than that, 60 years old when the therapies are initiated, we're talking about this line where nearly half of the people keep going, and so on. But here's the real kicker. This is a computer simulation, and so, of course, you can argue, well, is it over-optimistic, is it over-pessimistic, whatever. It's ridiculously over-pessimistic. This is the most extraordinarily cautious simulation you can imagine. Why is it cautious? This up here determines why it's cautious. We are suggesting that actually we're doubling the efficacy of these therapies only every 40-odd years, 42 years. Now, that's the distance between Lindbergh and Concorde, if you want an idea of how to think about that. It's completely ludicrous to suggest that it would be this slow, that progress in this would be this slow. And yet, as you can see, it's still good enough. It's still good enough to deliver longevity escape velocity in spades. So it's completely inescapable that we will, with the most ludicrously high probability, have a genuine indefinite lifespan as a result of breakthroughs on what sounds at first sight to be a rather modest scale, something like a couple of decades of additional life conferred on the middle age. This is the sort of thing it means if we think about lifespans. This is the sort of thing that gets me into real trouble with other audiences. At the moment, the world record lifespan is 122. Jeanne Calment died in the south of France about 12 years ago. She had some wonderful quotes when she was asked, "What's your secret?" She said things like, at the age of 120, she said, "I gave up smoking when I was 117. That's the truth. She did say that. This is an interesting statement. We will not get anyone aged 150 until we get robust human rejuvenation, this initial 30 years of life extension. But once we get it, the hard part's done, and so there's going to be an awful lot of people waiting in the wings, not much younger, that are going to be able to benefit thoroughly from these things indefinitely, and we're going to get to ages like 1,000, because that's the sort of age that you and I would already live to if we only died at the rate that we currently do as young adults. In other words, of causes that young adults actually do die of, like accidents and so on. That's what it means. And of course, we can make a similar statement about average lifespan. This is what it doesn't mean, and this is the sort of thing that people tend to go away with when they are predisposed to not listen to what I'm saying. They say, well, okay, immortality is by definition, not the ambit of technology. This whole longevity escape velocity thing sounds awfully like immortality to me. Ergo, this concept of of applying regenerative medicine to aging, which is what sense is, must be science fiction. And of course, this is not what you and I would call logical, but it doesn't stop an awful lot of people who should know better from saying it. And this is the sort of thing that some of my more strident critics tend to say. I've picked out a couple of British people here because these are good friends of mine sometimes. This is the sort of thing that is said. Richard Farragher is a rather witty gerontologist from Brighton, and he was introducing me, giving a talk about a year ago, and this was how he introduced me. I thought that was pretty funny. But the fact is, this is what I actually think. This is the title of a paper I wrote about 4 years ago that really put the cat among the pigeons, because it really said that these people are not just protecting their own careerist interests, they're actually doing serious harm to our ability to save lives.